Let's go ahead and get started. Hello, everyone. My name is Julia Matevosian. I'm a Chief Engineer at the Energy Systems Integration Group. I would like to welcome you to our first webinar in 2024 ESIG Monthly Webinar Series. And with that, Happy New Year, everyone. For those of you not familiar with ESIG, we are a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities in support of energy transition. We do this through workshops, tutorials, webinars, blogs, working groups, and task forces activities. And we are also producing technical resource materials. If you are new to ESIG and you like what you hear, I strongly encourage you to follow us, and I think you will be pleasantly surprised. ESIG membership will give you an opportunity to participate actively in all of our working groups and task forces. You can find us on web at www.esig.energy, as well as on LinkedIn, Facebook, Twitter, and YouTube. ESIG also serves in a leadership role with the Global Power System Transformation Consortium, the GPST, whose mission is to bring together key actors to catalyze a rapid clean energy transition at unprecedented scope and speed. ESIG leads Pillar 1 of the 5 pillars, which deals with research agenda for system operators. For more information on GPST, you can go to www.globalpst.org. Just a few logistical matters before we get started. All phones will be muted for the duration of the webinar to avoid unnecessary distractions. For Q&A, we're using Slido platform. So to ask your questions, please go ahead and go to slido.com and enter ESIG 25 as an event code. The instructions will also be posted in the chat, and you can see them as well on your screen. In Slido, you can use thumbs up button next to the questions to allow you cast your vote and help us prioritize the questions. We plan to save 10 to 15 minutes for Q&A at the end, and then we'll wrap up at the top of the hour. An email with the link will be provided once the video file has been posted, and we also plan to provide short responses to all unanswered Q&A questions that were asked during the webinar. So please go ahead and don't hesitate to ask your questions in Slido. All right, so turning to the topic of today's webinar, modern power systems are becoming increasingly dependent on weather. It's not a secret for anyone anymore. In early December webinar, you've heard from Justin Sharp on importance of good weather data sets for power system planning. And today we're continuing this topic with NOAA's 3-kilometer rapid refresh weather forecasting models and renewable energy forecasts. The National Oceanic and Atmospheric Administration, or NOAA, is a home to the National Weather Service, or NWS, which runs numerical weather prediction models operationally and provides the output free to all. These forecasts are used heavily for by energy community, and the webinar will include discussion on short-range weather model used by NWS, and we'll cover some of the changes that have been incorporated into the model that were motivated by energy community. So I would like to welcome our today's presenter, Dr. Dave Turner, who is the senior scientist at NOAA Global Systems Laboratory. He received his PhD from University of Wisconsin-Madison in atmospheric science in 2003. His research interests include understanding the processes that control the evolution of the atmospheric boundary layer and its interactions with the Earth's surface, radiative transfer, microphysics, and remote sensing. He is also manager of NOAA's Atmospheric Science and Renewable Energy Program. Just a short reminder, once again, to use Slido on slido.com to ask your questions. The code is ESIG25. And without any further ado, let's go ahead and get started. Dave, now turn it over to you.
Well, thank you very much for the kind introduction and invitation to speak to this group. You're able to see my slides correctly and hear me okay?
Yes,
okay,
I can see and hear you.
Wonderful. So, as was indicated, just giving you, thought we'd give an introduction about some of the weather forecasting development that we've done within NOAA, especially on what we call our rapid refresh modeling systems, and the role they can play for renewable energy forecasts. So I think the motivation this group will understand it well. The fifth National Climate Assessment was recently released just a couple months ago by the government. And, in that report, there's a wide range of topics. It's a very interesting and, thought-provoking assessment. But we can see that through climate change and just, over time, we're going to have this increasing amount of demand for electricity over the next 30 years. In some states, it's going to grow by, up to 75%. Others, few states maybe a little bit less. But as we look at trying to figure out how we're going to meet that demand, the assessment looked at this and really sees the continual growth in wind and solar being really important to meeting this increased demand, especially as we try to reduce the amount of carbon emissions that our electricity generation is generating. And so if we look at the levelized cost of energy, onshore energy on the left and solar energy on the right, and you start adding in levelized costs of other sources, this would be the cost of nuclear for a megawatt hour. You can see the cost of coal, the cost of a combined cycle gas turbine, and you can see with those costs that already the wind and the solar generation, especially at an industry type scale, is less than that. So we can see that just financially, we're going to want to have more renewable energy generation added, because without having to pay for the fuel, that's quite useful. Of course, these sources of energy are variable depending on the weather. But if we look at the onshore capacity of wind, it's been growing steadily with time. The utility scale solar is growing even more rapidly with time, especially. You can see that currently the US fraction of those global capacities are relatively small, 13% and 4% as of the end of 2022. But we're expecting just more growth, almost exponential type growth in this area. The current Biden administration has some priorities for us. And so they stated when they first took office that they really would like to see an incredible increase of offshore wind generation installed before 2030, 30 gigawatts of extra power generation. And they anticipate that we would get about 45% of our total electricity from solar generation by 2050. Of course, because this is very dependent on the weather, we need to have better weather forecasts in order to really make that electrical grid more efficient and resilient. And, with the climate changing, we need to be able to prepare for that. So NOAA, through its research and through its operations, provides foundational weather forecasts. We make these forecasts available to the entire community, not only the energy community or the weather community, but all communities. And these can be used to make decisions about what type of mixture of sources you want to use for your generation, or even decisions about how much demand you may anticipate, because it's really complicated with the additional behind the meter generation. We recognize, as researchers, and I'm the chief scientist of a research laboratory, that we need to continue to improve our treatment and our representation of processes in the boundary layer, how clouds and smoke is represented, and precipitation. All of these have impacts on energy generation. And so our Atmospheric Science for Renewable Energy program is a multi-laboratory program that is conducting field campaigns, analyzing those data, taking those data and translating them into improvements in these numerical weather prediction modeling systems. And then we have regular cadences where we transfer these improved models into the National Weather Service, where they are run operationally for the benefit of all. And so I tend to think of 4 different timescales when it comes to renewable energy forecasts and predictions. There's very short range, seconds to hours. And I mentally think about keeping the power and voltage supply stable, and about making the grid just more stable in these short time periods where you might have perturbations to the generation. We have the time scale as sort of the hours to days, and this is really using these short-term, 1 to 2 day weather forecasts to really figure out how to generate, how to decide on your generation sources as you're trying to figure out how to meet tomorrow's demand. This can really help make the electrical grid more efficient. And we've already shown through various publications I'll speak to in a moment that this can result in significant cost savings already by continuing to improve these type of short-range prediction models. There's sort of the days to months, what we would call the medium range to sub-seasonal range forecasts. In many ways, this is to identify when you might have a period of time an extended period of time where there'd be very low wind or very low solar, so you would be a renewable energy drought. When you might decide to do your maintenance because it might need some time to schedule the resources, the cranes, the other infrastructure you might need to do your repair or maintenance. And so you'd like to do that when you're not in a period of one of those droughts, perhaps. And so this helps to make the grid more resilient. And then there's that longer sort of decadal-like predictions that might, give you a sense of how the renewable energy resource may change with time, especially in light of climate change, how many additional damaging weather events that may, you may have to plan for when you build your new infrastructure, how that might change with time. So really that sort of decadal time scale is to help make better decisions on infrastructure. And NOAA really has a role to play in all four of these time scales. For the purposes of this talk, I'm going to really focus more on the hours to days, that short range weather forecast, and we'll come back to the other time scales briefly at the end. So what is numerical weather prediction? So first we have to think about what's weather and what drives weather. Well, really, weather is driven because we have this differential heating of the Earth. We have the solar radiation impinging on one side, and so it's heating one side of the planet. The entire planet is emitting energy to space. And so in the end, climate is about the balance of the incoming energy from the sun with the outgoing energy that's emitted by the planet. If that was identically the same, then there would be no change of climate. But what we see is we're changing our atmospheric composition. And so the outgoing long wave radiation is not balancing the incoming. And so we're seeing this gradual heating of our globe. Well, this differential heating, you can think of the atmosphere as a fluid that's rotating on this sphere. And so as this sphere rotates, and so looking at the plots on the right, I'm looking at it from above the North Pole, we can see these patterns, these wave patterns that start to develop in this fluid that is the atmosphere. And sometimes you can have a very uninterrupted flow pattern that looks reasonably spherical as the winds zonally move around the planet. But because of the differential heating, we can start to see waviness forming in those winds, where you can start to see the development of high pressure centers and low pressure centers. Those waves can get more, pronounced, and you can see the development of low pressure centers that maybe get cut off or extend deeper into the mid latitudes and become a cutoff low that can then continue to circulate also. So those are sort of the spatial structures, but we also see these type of circulations happening vertically. And so this cross section sort of shows an equator to pole cross section, and you can see that this sort of differential heating creates these well-standing circulations vertically, where you see rising area of the equator that sinks around the mid latitudes around 30 degrees. That sinking drives another vertical motion, series of the Ferrel cell in the mid latitudes, where you can see rising roughly in the 60 degrees. And then there's, of course, a polar cell that rotates in the other way. All these rotations, these whirls actually often generate smaller whirls, and those smaller whirls keep generating smaller and smaller eddies from that until they finally go off and dissipate. And so that was a classical, poem almost by Lewis Fry Richardson back in the 20s about weather. And so we can see, when we start seeing these development of all these motions, we can see what looks like a very typical frontal weather pattern in the US. And so this is just an example that you would draw from any sort of weather map, where you can see this low pressure center centered over the Great Lakes, with warm air kind of up into Canada, and then this cold air swinging by through the central plains toward the southeast. And all of this is this benefit of the motions in the planet. But it's not only planetary scale. We see this differential heating, which initially is caused by the sun and heating the planet on one side and the infrared radiation cooling. We can also see differential heating associated with phase change in the atmosphere. So these motions can often cause the air to be lifted, like as a cold front advances. That colder air is more dense, and so it tends to lift the warmer, more moist air up in the atmosphere. But as air gets lifted, it cools adiabatically. That change of phase, as that water vapor condenses into liquid and forms a cloud, actually warms up the air where that formation happened. And so that can create vertical motions there as warm air wants to rise and cold air tends to sink. That type of vertical motion, if strong enough, can create these supercell type storms, where you can see just an awful lot of motions happening here, with precipitation that creates cold downdrafts that work to feed storms. So all this type of processes have to be represented in a weather prediction model. And so ultimately, weather prediction models have to handle a huge range of scales, from planetary scales all the way down to microphysical scales, where you see the condensation of water vapor into cloud droplets and the formation from droplets into ice particles. And so when we look at all these range of scales, you'll see the climate models tend to operate with resolutions, grid vertical spacings of about anywhere from 25 to several hundred kilometers. Global numerical weather prediction models tend to work on the scales from about 5 to 6 kilometers up to about 50 kilometers. We have regional NWP models that end up going from order 1 or 2 kilometers up to maybe 15 kilometers resolution. And then in our research paradigm, we have large eddy simulation models that we can use. So how do we do this? We have these range of models that we're using. For the day ahead problem, I'm going to really be talking about regional NWP models, but for the moment, let's look at how do we use these models to actually look at the weather. So first, what we do is we take a globe or a regional globe, and we're going to have to break it down into boxes. So we put a grid on it, so there's some sort of horizontal grid that breaks up the region into these horizontal boxes, and then there's also a vertical component. And then each one of these boxes that are kind of illustrated here, we need to be able to specify all the variables that are sort of important to weather: temperature, humidity, cloud properties, winds, precipitation. And we need to figure out how to move those variables from one box to its neighboring box, whether that be horizontally or vertically. And so there's a lot of actually work associated with that. And so ultimately, what the language is that we use in NWP are mathematics. We have all these partial differential equations and other equations that sort of describe the evolution of these different variables as they evolve within the box and as they move from one box to another. But we have to represent momentum. We have to have thermodynamic relationships. We need to be able to make sure we conserve mass and moisture and energy. We need to be able to represent clouds and precipitation. And of course, the whole problem started with representing the solar radiation impinging on the planet and the infrared radiation going out. So we have to represent radiation too. Many of these things are actually done through what we call parameterizations. When you look at some of these processes that are at work, and not just some, many of them, they turn out to be much finer, working at scales at much finer resolutions than whatever that horizontal model grid that we use. So you break the globe or the region into these horizontal boxes and then these vertical boxes. But most of these processes, such as turbulence or clouds or even convection and radiation, they're working at scales much smaller than that grid spacing that you used. And so, I'm just showing this top figure. This is roughly a 5 kilometer cross section. This is showing turbulent mixing of water vapor in the lowest 2 kilometers of the atmosphere, where dark colors are drier and warm colors are moisture. And so you can see there's a lot of fine scale structure that we're trying to have to resolve in a model that maybe has a 3 kilometer grid or a 10 kilometer grid. Similarly, the lower picture on the right sort of shows various microphysical processes that are happening within a strong cellular cloud, where you have water vapor coming in from below with aerosol particles. These things condense. Maybe those droplets connect to each other, coalesce against each other, collide against each other. You're draining air from the environment. These particles are growing, ultimately maybe turning into snow or other ice particles like dropple, and falling out of the sky. And as they fall out of the sky, they have, again, opportunities to collide, intersect, break up, evaporate, etc. So there's all these processes we're trying to represent in these models. And if you have errors in them, it drives errors in your forecasts. And so ultimately, because we can't resolve those processes, but we still have to represent their impacts, we need these parameterizations, which are ultimately the simplifications of the physical processes. And so we've been working continuously for the last many decades to try to improve how we represent all these processes in our parameterizations. Certainly increasing the model grid spacing helps. If you were to take a grid that's 10 kilometers resolution and you were to make it 5 kilometers in resolution, then you don't have to represent quite as many processes through the parameterizations. However, this is where it really becomes computationally expensive, because if you double the model resolution, it turns out that makes the model 2 to the 4 times. So there's 3 dimensions, X, Y, and Z, as well as time, so 4 dimensions. Every time you double the model resolution, you make the model 16 times more expensive computationally. So there's a limit to what resolution you can really use. So when I look at an NWP system, there's really three large-scale components to it. You need to have what we call the dynamic core, which is basically the equations and the framework to move the air around from cell to cell. You need to have a physics package that represents all those microphysical processes that are happening, so basically the parameterizations. And then the third bit that you really need, it's really important for weather, is you need a data assimilation scheme. You need to be able to initialize each one of these boxes on this globe, which is broken up into boxes spatially and vertically, with specifying the temperature, humidity, winds, clouds. Into every one of those boxes, you need to be able to specialize those initial conditions. And we just do not have the observations to do that. We have a powerful observation system, in the weather community with satellites and surface-based observations, but it's not nearly enough to start representing and to provide us the information we need in each of those cells. So what are we doing then? Through that data assimilation process, we're basically trying to find mathematically the best fit between a model field and the observations. Now this comes into this concept of rapid refresh. So in a rapid refresh, what that really means is you're going to reinitialize the model very frequently. So you want to use the most recent observations. So you have the best sort of information awareness that you have at the moment. And so the data assimilation is computation expensive. So there's strategies on how well you do this. In NOAA's rapid refresh system, we do this sort of 1 hour restart. So every hour we restart the model and provide a range of forecasts from it. Currently, we have these rapid refresh models with two dimensions. Basically, it's a pair. We call it RAP for the 13-kilometer model that covers all of North America. And then we have the high resolution rapid refresh, which we pronounce HRRR, which is at a finer grid resolution. It's a 3-kilometer model that's just over smaller domains. We have to do it over smaller domains because, again, the computational expense of doing it at that high resolution is tremendous. And so, being part of the NOAA and the National Weather Service, we have to provide these products to much larger than the energy community is to the weather community, the severe community, transportation, etc. And so that's why we have these two domains to try to cover both Alaska as well as the continental US. All this output is available on the cloud. You can go to the NOAA, the nod, which is you can easily Google that and get these data. It's freely available to everybody. But so in addition to all that, we're trying to, of course, improve our forecasts and improve our scale for missing processes. So one of the things that we added recently, we actually were developing it back from 2016, 2017 is when we started that development, and it became operational in December of 2020, was the addition of adding smoke and the impacts of the smoke to our weather forecast systems. And so we actually identify the fires using satellite data, and the satellite data give us a sense of how intense the fire is, and knowing the intensity of the fire, how hot it's burning, you can predict how much smoke mass to put in the model and at what height you should inject that smoke mass into the model. And then we use the dynamic core to basically allow that smoke to move around in the atmosphere. We allow that smoke to interact with the solar radiation through our radiation parameterization so that we can actually see what the impact is on the surface solar radiation, for example. And we have seen that including smoke has greatly improved our 2-meter temperature forecasts. And that's really important, and it turned out to be highly, made various communities such as the air quality community, the aviation community, and of course this community very excited because we do include that treatment of smoke. We've made a number of other improvements to the high resolution rapid refresh over the years. The ones in brown are basically improvements that we've made to the parameterizations. The first 3 are sort of ones that we've made at a higher level, to the modeling system because maybe we've had a bigger computer and so we can do longer forecasts out to 48 hours. We've changed the way the data assimilation works to actually allow it to have higher spatial information, to include more spatial information through the data assimilation process. Both of those were only achievable because we've continued to acquire larger computer systems that we can use for these forecasts. But we made a lot of these parameterization improvements primarily using field campaign data. We've improved our 80-meter wind speeds by anywhere from 4 to 10%, depending on the time of day. We've decreased the bias in our solar radiation at the surface over time by increasing the clouds and improving our treatment of clouds. And all of this sort of improvements to the parameterization lead to these better forecasts. So for the energy community, and I'm going to show an example here from the wind energy community, capturing ramp events where things change rapidly with time, such as wind speeds increasing dramatically over a short time period or decreasing dramatically over a short time period, really important to capture. And so the treatment and the way we're representing some of the processes within the HRRR system allows us to catch a ramp event like this, where other NWP models just had no sensitivity to that event. And so we've heard from colleagues in Southwest Power Pool about how valuable this is to their decision making as they're looking ahead with their, anticipating what type of generation they need, for tomorrow. Taking a look at this, we did a side study working with some economists up at Colorado State University to evaluate the economic impacts on the energy sector by having these improved wind forecasts. And so we did this by comparing HRRR version 1 versus HRRR version 2, or HRRR version 2 versus HRRR version 3. To really make it a fair comparison, we had to have the two versions of the model running on the same period of time, which we do when we have the transitions as part of our transition from one model to the others. We have usually about a year of data where the models are operational at the same time. But we considered both over prediction, where the model forecasts too much wind, and therefore, the ISO may have to acquire power from somewhere else, as well as under prediction, where the model forecasts too little wind, and so therefore the ISO is using more fossil fuel than needed. Those costs are not symmetric, and so this study looked into that. And what we've done, there's a lot of assumptions having to be made here, but assuming that the decision was based purely on the HRRR forecast, using version 2 relative to version 1 would have saved the energy community nearly $500 million a year. And version 3 versus version 2 would have saved roughly $230 million a year. And what was very fascinating with this is that the impacts on these were different. So version 3 had a much bigger impact on under prediction, where version 2 relative to version 1 was just overall quality generally. As we continue pushing this forward, we realize that we're starting to see more behind the meter generation happening all the time, especially with solar. And we're as the administration forecasts, we're going to see the continued growth of utility scale solar too. And so you have both this, the same thing, the downwelling solar radiation providing both generation for the consumers as well as generation by the utilities. And so what we're concerned about, and I know many in this community are, is what if we have a big weather event like an extensive cloud deck, smoke, or dust that can strongly impact the solar energy. Therefore, the ability, the demand is going to go up because the behind the meter generation disappears, but then the ability to meet that demand goes down. So we really have a strong emphasis within our renewable energy program here to be able to improve our forecasts of these type of events, so that there's more guidance available longer, so you have more information soon to be able to handle these type of events. So in addition to some of the solar energy, we continue working with the Department of Energy on what we call these wind forecast improvement projects. We've conducted 2 of these WFIP campaigns, already in the past. One was focused on initializing the model, improving data assimilation techniques. The other one would focus on the challenges in complex terrain where we often have turbines installed on mountains and ridges and in valleys. The third one is really targeting offshore wind energy characterization. And so looking to improve and understand atmospheric processes offshore, especially off the US East Coast. And so we can incorporate some of this new understanding into our foundational model forecasts. We are currently starting a field campaign now that is already underway, really with the goal of improving our forecast for offshore wind off the East Coast. The East Coast creates lots of challenges for us. I mean, it's much different than what we see in the European offshore generation areas. And that difference is largely because there's a huge landmass, i.e. the continental United States, just to our west. And so we often, in the wintertime, we will have cold air. The air gets cold because it's in contact with the United States, that then detects over the warmer waters. That's quite a different sort of environmental condition, near surface environmental condition. And in the summer, where the air that comes off the United States is actually very warm relative to the temperatures just above the ocean. And so you get these different these different temperature profiles, which changes the stability, that creates all sorts of interesting challenges with forecasts associated with low-level jets, with different sort of features in the wind that we're trying to capture. And then we have a complex coastline, which makes that also challenging to represent. So really, those are some of the key science issues. We've deployed instruments out here just south of Martha's Vineyard. The dots kind of indicate where the observations will be collected. Probably the key thing here is we have an instrumented barge that will be out for several different couple-month periods this spring and then this summer, right where the wind lease areas are being negotiated. We already have some instruments, some turbines being put in the water already in one of those lease areas. A variety of different instruments from NOAA, as well as the Department of Energy, Woods Hole Oceanographic Institute, and a variety of different universities are participating. So I want to take the last few moments of this presentation to give you an overview of what's coming. So I've spoken a lot about the high resolution rapid refresh, and what is NWP in the first place, and what are some of the things we've been doing moving toward this new forecast modeling system. So the motivation here is in our operational numerical weather prediction suite, which is run by the Weather Service. We actually have a lot of different modeling systems that are doing very similar type of applications. And so if I just focus on the green areas here, you'll notice that we have multiple regional modeling systems that are all working to provide regional forecasts over the area. And we want to simplify this. Right now, if you have all these 21 different modeling systems, that requires 21 different teams to sort of maintain it. And it's sort of splitting our effort too much. So we want to simplify that into a simpler and smaller number of models. This is this unified approach. So from the regional perspective, this sort of storm scale, 3-4 kilometer resolution type things, we want to reduce those 7 current operational systems to a single one, because currently those 7 systems have different representation of the physical processes, i.e. different parameterizations. They're using different data assimilation approaches, running over slightly different domains with slightly different forecast lengths. So we want to unify this, get it down to a single 4 kilometer-ish modeling system. The decision was made a while ago to use a different dynamic core than what we've used in the HRRR. Again, those 7 models are using different dynamic cores, so we need to adopt a single one. The dynamic core is you can consider it the heart of the model. It is the thing that moves the air masses, which is all those things from one cell to another. And so we've already made great progress adopting FP3, that dynamic core, into our global forecast system and the global ensemble forecast system. And so now we're doing it into this regional system, the rapid refresh forecast system, which we pronounce RUFUS. The development started many years ago. It's a collaborative effort with several NOAA labs and Weather Service. And we're going to use the physics from the rapid refresh, high resolution rapid refresh models. So we already, in many ways, this model is going to have similar performance characteristics to what you may already be used to. But we're going to need a larger domain to start covering other areas. And so here, reminding you what the RAP and HRRR domains look like, this is the same slide as before. This is going to be the RUFUS domain. So it's a single domain covering a good portion of North America. You can see it's extended to be able to provide operational support over Hawaii, to provide support over the Caribbean, to provide larger areas so we can see impactful weather events like hurricanes off the East Coast, atmospheric rivers off the West Coast, and a little bit more information about Arctic air masses that move from the north over the continental US. But FE3 is what we call the cube sphere configuration. So it's Earth, its ESG grid is very interesting grid and gets finer at the boundaries. We're going to project that grid to make it more easily to use. So we'll project it onto a rotated lat lawn. We're also going to have some sub cutouts so it can sort of mimic output you may already be used to, such as a HRRR-like domain out of here. But the model it's a very big domain. We're generating much larger data files in the native forecast and really challenges it. But there are other challenges associated with RUFUS. We're going to, in both the RAP HRRR system as well as the RUFUS system, we have to start from the large domain, the global forecast system, which is representing the circulation over the globe, and then use it to drive these regional models. So before, we took the global forecast data to drive the RAP, which then drove the HRRR. So we had 3 integration domains. We're moving toward with RUFUS is just 2 distinct domains, going from the global forecast system to the high resolution RUFUS domain. We're going to have a higher vertical resolution, especially in the lowest parts of the atmosphere, where we're going to have roughly double the vertical resolution in the lowest several kilometers, which will help represent things like clouds and turbulence in the boundary layer. But the physics, although it's based on the HRRR physics, those physics schemes, those parameterizations have really been updated over the last several years. And so you can see the schemes here if you're interested, but really improving the performance and representation of the physical processes with those parameterizations. We will continue to have smoke within RUFUS, although you can see with that larger domain, maybe we'll be able to do a better job providing a longer range smoke forecast. Again, the smoke doesn't evolve chemically, but we do allow it to interact with the radiation and ultimately, impact those surface temperatures and the downwelling radiation at the surface. One of the things that's important also for this is we're going to include dust into this first version of the RUFUS, both fine and coarse mode, and that's really could be quite important for visibility. And there are times where dust can have a significant impact on the downwelling solar radiation. Other features, again, we assimilate a lot of different observations to initialize the model. Profiles from radio songs and aircraft, a few remote sensors, radar, operational radar data and lightning data from satellite turn out to be extremely important about getting the convection right. Surface observations, both from surface met stations on land and on buoys and ships, and of course, a lot of other satellite data too. We're improving our data assimilation method to try to remove a bias that we realized afterwards was in the DA system that was used for the HRRR. We're continuing to couple the model well with the land surface and to do this what we call moderately coupled data assimilation between the land and the atmosphere to keep the land surface conditions about right. That turns out to be really important to keep the clouds right. Continuing to actually initialize clouds initially from the model. So you have the clouds in the right place when you initialize the model. That way your forecasts are actually start off in a good place. And adding a lot of diagnostics after the model. So we predict the motion of the fields and the evolution of the fields, but after we get done, we can still, after the model is done, diagnose other things. So we're going to try to add, for example, a metric that sort of says how variable we expect the downwelling solar radiation to be, or give you a better estimate of what the wind gust potential may be at the surface. An important part of RUFUS, though, that I really want to emphasize is it's going to be an ensemble prediction system. We're actually going to have 10 members, each doing 48-hour forecasts, which you could then use to do some probabilistic studies. So this kind of gives you a little bit of a map here. So the model, again, is initialized every hour. And what we have is an ensemble data assimilation system, which allows us to use the observations as well as we can. And then we're going to do these deterministic forecasts. So every hour, we'll do at least an 18-hour deterministic forecast. And then 4 times a day, we're going to have a 60-hour deterministic forecast. Well, at the same time we do those longer deterministic forecasts, we're also going to run 10 members of this model to do a 10-member ensemble out to 2 days, out to 48 hours. And so you'll get some probabilistic information. And so how can you use this probabilistic information? So this is an example of a tool that's being developed here where you can look at this. This gives you a probabilities on the right-hand side, in this case, of low-level cloud cover being above 50%. And so you can see the warmer colors are higher probabilities of cloud cover over this region of California. You can look at this one way from on the ensemble system to look at probabilities of something happening. We can also look at timing of events. So this is going to be the sort of the 10% metric on when you expect clouds to onset, to start coming in. And so you can see the purple colors, the cold colors, are really early in the forecast, where the warmer colors are, showing that low cloud getting there much later in the forecast. So you can get some timing information of when you might expect winds to come. You can get some idea. This is on wind speed in the plains, getting what's the mean timing of when the wind speed might be above a cut-in threshold winds. And so you can see in this particular event that I've picked that the mean timing of when the winds would achieve a cut-in threshold would be somewhere around 38 to 40 hours in the forecast. But you can get a sense of what's the earliest timing that you might start seeing winds above that cut-in threshold or after. So it's sort of in summary here on RUFUS. This really is a major upgrade over the HRRR, a larger domain, longer forecast lengths. It's an ensemble system. We're trying to include, improvements to the physics that allow us to be scale adaptive so that, down the road, we can have an even higher resolution, 3 kilometers, continuing to add capability to smoke forecasts by, and adding dust forecasts, which is going to improve our downwelling solar radiation. Better data assimilation, having this coupled data assimilation at high resolutions, storm scale type resolutions, so we can do a better job with initial conditions, which is really important for those shorter range forecasts out to even 48 hours. But what we're seeing is our verification statistics look very good. They're very close to the HRRR verification, even though it's such a major change in the modeling system. We're trying to match or beat the HRRR verification scores. So what's the timing of this model? We're really close to freezing the code. And after the code is frozen, then we go through sort of a prolonged period of science evaluation, where various different stakeholders within the Weather Service evaluate the capability to model in their particular area of expertise. And if it passes the science review and the code evaluation, then it would become operational in early 25. I should say there are some challenges with this RUFUS about the convective storm scale and getting the storm structure right, which is really important for the severe weather community. We've traced that to actually the dynamic core and its behavior. We've been able to mitigate it to some degree, but what's maybe important for this community to know is that as part of the risk mitigation, the RAP and the HRRR system will remain operational even after RUFUS becomes operational. And so we'll see the other models retired. So if you're using the NAM or one of the other nested models, those are going to be retired, but the RAP and the HRRR will remain operational even after RUFUS does. So I think just with very short concluding remarks here, there's lots of reasons why we need to continue to transition our energy system and continue using renewable sources. And certainly weather forecasts are very critical for this industry and for this application. Really working on higher resolution models and the rapid refresh report for that day ahead. And I think I've driven that point home through the renewable energy efforts here in NOAA. We are going to start looking really much more at those global modeling systems, which are ideal for that week ahead challenges. They're sort of for the maintenance type of questions, the renewable energy droughts. And of course, NOAA's been providing climate model output for a long time. And those are really ideal for looking at infrastructure challenges and how to analyze how the resource may change with time in a certain area and about severe weather. So with that, I'll stop and take any questions.
Thank you so much, Dave. Very interesting presentation. Let's go ahead. David, there is a little bit of feedback from your mic, so maybe you can mute while I'm reading the question and then unmute again when talking. Sorry about that. All right, so the first question from Justin Sharp. Please, can you provide some color about what goes into calculation of the economic impacts you showed?
Yeah, absolutely, Justin. Good question. The economists had what they call these, so with a lot of economic models, they're semi-empirical. So they're based on principles, but they often have some empirical constants. And so these models that the team at Colorado State used were calibrated over many decades of sort of economic data from different regions across the US. And so with those economic models, then you can drive them with, for example, decisions like this about how much energy you might get from wind versus how much you need to go get from other sources. And they're sort of like perturbation type studies. And so they can propagate that through your economic models and see the impact all the way down to the ratepayer. And so the numbers I presented were for the utilities, but those studies actually go all the way down to the consumer and how much savings there would be for the consumers. And so that was sort of on the order of many tens of millions of dollars per year to the consumer level. And it works through the taxes and other aspects of that. So there's quite a lot of complication there. Best I could do is probably refer you to that paper.
Right. Thanks about that. The next question is there potential for RUFUS reforecasts to be created, for example, from 2022 and forward? This would allow forecasters a longer history to train models with.
So I should say, we hear you. We really would love to have this too. You can see the size of the RUFUS domain. It is, and there's a lot of reasons to have a domain of that size and to have an ensemble prediction system because of all, the needs of all the different stakeholders, again, ranging from the severe weather community to aviation to this community and agriculture and transportation. All that said makes the model really too computationally expensive to do a very significant historical reforecast. That said, there is a strong desire, and I'm going to anticipate a future question about, there's been a lot of advances lately about using machine learning to do basically data-driven weather predictions. And so we're very interested in NOAA about seeing and developing some high resolution, some order 3 kilometer type machine learning weather prediction modeling system like that. And so to do that, well, we're going to have to generate a longer reforecast that we can use for training. So we're in discussions about how that can be done right now. The compute power just does not exist within NOAA to do it, but maybe we can collaborate with the Department of Energy or some other agency to get there.
Thank you. The next question is how, sorry, question just gets folded up and up, hard to catch it. How valuable do you think meteorological observations from wind and solar projects might be in the assimilations process for HRRR and potentially RUFUS?
So I really would like to establish more data sharing agreements with this community on that. We're tending to, what's really important for these operational models is that the two things, the observations are known quantity, known and understood quality. And secondly, that they have very timely delivery, so they cannot have much latency, especially when we're restarting the model every hour. We need the observations to ultimately be to us within 5 minutes of collection. Otherwise, they don't get used. So if we're generating a forecast, for example, at 3 p.m. today, we need to have that forecast running by 3:05. If we're initializing the model at 3 o'clock, it needs to be running at 3:05. So that means all the observations have to be to NOAA by 3:05. Otherwise, they're not going to be included. And so that data latency really is a challenge for many. And also the known and reasonable quality becomes a challenge, because we've seen in the past where we're using observations and suddenly the quality goes south and then the entire forecast goes south. And that's something that we have to be very sensitive to.
Next question is for SPP. Are the better results that you've shown primarily because of high resolution or specific parameterization such as smoke?
So that's a great question. Part of our, I do interact regularly with the different, basically ISOs out there in conversations, primarily through ESIG, which is awesome and great. Their decision-making process, what different modeling systems are being used in their decision-making process, is, it's sort of their trade secret. And so I don't necessarily know what modeling systems they're using, but presumably they're using, since right now NOAA has 7 operational regional models that are running somewhere between the 3 and 4 kilometer resolution. I'm assuming multiple of those systems are being used as part of that decision-making process, together with perhaps models run by themselves, as well as European providers. So I don't really know what other resolutions are there, but I would assume that, for example, the results of the wind ramp included other sort of 3 kilometer models as part of that decision, but I don't know for sure.
The next question actually related to ramp events. You mentioned the value of using these models in forecasting ramp events in wind power. How do you quantify the ability of a model to capture ramp events?
Excellent question. We actually have a study going on right now. It was conducted by students actually that I hired over last summer and then the summer before, where we're trying to use the observations across the Great Plains, for example, to look at how the wind speeds change rapidly over a short time period. Do we see, it's not just the wind speeds, put it through basically a model that predicts generation, and say, how often do we see a change of, for example, 40% change of produced power over a 2-hour period? If we define that as a ramp, then we can very easily start to compare the model's ability to identify and predict that ramp event relative to the observations. Now, in this study, which we're going to actually present next week at the annual American Meteorological Society meeting in Baltimore, we don't have enough sort of hub height measurements to do that. So what we're using is the sort of the generally available 10-meter wind speeds that are collected at call the weather service ASOS stations as a surrogate for the winds at 80 meters. So the assumption is if there's a wind ramp at 10 meters and we can capture the wind ramp events at 10 meters well, that we're probably going to be able to do it at hub height also. It's an assumption, but that's how we're trying to characterize that. And one of the things that we are seeing in that study is her version 3 was pretty good, or her version 4 is actually markedly better than her version 3, with improvements in some of these ramp skill scores of, anywhere from 10 to 20%, sometimes as high as 30, depending on the season and the time of year.
Okay, thank you. Sounds good. Do you expect the inclusion of dust and smoke to also capture the impacts of pollution in the modeling of solar radiation?
Very much so. One of the ways we, when we look at adding smoke and dust into our modeling system, how do we ultimately verify if we're doing a good job? So one is comparing to downwelling solar radiation observations themselves. And then the second way is actually comparing, for example, to PM 2.5, that's particulate matter that are 2.5 microns or larger, which is, there are these networks across the US that sort of measure that PM 2.5 concentration, because that's a really important air quality indicator. And so we're using those two things together, as well as even the 2-meter air temperature, to give us a sense of, is our inclusion of smoke and dust, are we doing a good job? You can imagine, even if we have the fires in the right place, if we inject smoke, for example, in the wrong level of the atmosphere, maybe it's too high and it doesn't get ejected to, the right areas, or maybe it's too low and it ends up, basically being deposited on the surface and removed from the atmospheric model too quickly. So, there's lots of challenges in actually representing, the treatment of smoke and dust in the model properly, but that's kind of how we evaluate it. But I always welcome from this community, if you see things our model's doing well or things that you wish our model did better, input on that, and at the ESIG forecast meeting is a great place to catch up with me.
Thank you. It was actually my question, how do you get input from energy community? But I guess you just answered that.
Yeah, I've been going to the forecast meeting regularly for the last several years, and before that was Stan Benjamin, who many of you know, and Stan was a regular participant even before, back in the VIG group, I believe is what it was called, the Variable Energy Group earlier.
Right, let's go to the next question. How long will the planned overlap period for her and RAP with RUFUS? How long will the plan, I guess, will be the overlap period for RAP and RUFUS?
Great question. So we're going to, freeze the code very soon and do some, some controlled retrospective studies in some different seasons. Those retrospective studies are just going to be, anywhere from 4 to 6 weeks in different seasons that we can use to share with the different stakeholders to evaluate it. The good news is even, let's suppose that RUFUS is blessed scientifically and becomes operational in the spring of 25, like I think it is. They're not retiring the RAP and the HRRR system. So those systems will run side by side operationally for several years until we get a RUFUS version 2. And RUFUS version 2 is probably going to be likely in the 2027 timeframe, would be my guess, because I've kind of indicated that we've identified challenges with RUFUS version 1 associated with storm structure that we linked back to the dynamic core. And this has caused great consternation within the agency for sure, because effectively what it means is if we want to really move the needle to continue to improve our ability to forecast severe weather, we have to change the dynamic core again. And that is, again, that's major heart surgery to a modeling system like this. And so we are, going to do that. And that probably means that RUFUS V1 and the RAP HRRR system will be running coincident for quite some time, multiple, probably at least 3 years, maybe 4.
Thank you. The next question is, given that the current HRRR has 3-kilometer grid spacing, is there a reason you are heading towards approximately 4 kilometers grid for RUFUS?
So actually the actual grid spacing on RUFUS is 3 kilometers. However, the way that dynamic core works is sort of its effective grid spacing is a little bit closer to 4. And this was something, again, not really understood well until we got deep in the development process to sort of realize that. But it's going to be output on a 3-kilometer grid. It's just sort of important for, again, as users. I mean, even the HRRR, when you have an NWP system like this, there's diffusion in the model. So two adjacent grid cells are not really independent, modeling. There's a sort of an effective resolution. And so on the HRRR, the effective resolution was about 6 times its grid spacing, or about 18 kilometers, 6 times 3. On the RUFUS, it's going to be about 6 times 4. So it's going to be about a little over 20 kilometers. But it is still going to be on a 3-kilometer grid.
The next question is, it's a good question. What words of caution would you give to power system modelers looking at using this data? Does that change for retrospective analysis looking back at, does that change retrospective analysis looking back at year 2020-ish?
Wow, that's a really great question. I mean, I think the thing is that, we have seen clear improvements in our ability to forecast the weather. Our ability to do a short range forecast, and give a 48-hour forecast of the weather today is markedly better than it was even 10 years ago. It's a little bit hard to quantify because it does depend on the exact event. What is the type of event that you're looking for? And what's challenging is that the primary purpose of a modeling system like HRRR and RUFUS is convective, to get convective scale, right? But there's so many applications where the higher resolutions, temporally, the higher spatial resolution is really important. This being one of them, and so I think we need to just continue communicating with each other, and when folks share in the community, when does the model work well? And I think that was some of the words that we got from SVP was, boy, they were really happy with how well it handled and forecasted ramp events in hub height winds. But how well do we do about getting precipitation? So one of the things I've learned about, and it took some time with HRRR version 4, is that it has a slight dry bias associated with the data assimilation system. And so it wants to evaporate snow a little bit quickly. So as one potential impact for this community is, does snow stick around as often as it should? An impact, for example, I don't know quite how you model and treat snow on your solar panels. That may attenuate the generation capability of those panels themselves. But the model is going to want to get rid of that snow a little bit too quickly right now. And that was a bias we learned well after it became operational. So I think we just need to continue sharing these experiences. We want to, really have an interactive engagement with you so that we can see what do you think are the problems in the model that we should work on and address, and we will prioritize them.
Thank you. I think this will be the last question. And Dave, your hope of having one to answer offline is not there anymore, because there are many more left for you to attend to after the webinar. A lot of good questions. So the last one is, do you think AI-based analysis of observations of the track of cyclonic systems to predict peripheral high wind trajectory will help?
Well, great question. I think we have a lot to learn about how AI systems truly work and at what level can we trust their predictions. And I think, explainability and trustability are really key phrases I'm kicking around and with my colleagues on when it comes to basically these AI data-driven models. I think we're going to learn a lot through them. But one of the challenges with this is how important are correlations among variables. So for the storm community, storm structure is really key to helping them decide what the impact of that storm may be on, and whether they need to issue a severe weather forecast or watch or warning type of thing. I think we have the same questions associated with the correlation of variables here, and how well do these data-driven models represent these correlations. The moment they don't seem to, they tend to treat these different variables somewhat independently. And so this is one of these things, is as we learn more about them, as the community building these AI prediction systems grows to include more meteorology and more people from the operational weather community, I suspect we're going to see rapid advancement here. So it's a little hard to guess, but my sense is the answer is yes. We're going to see probably a stepwise improvement in a decade or so when we start really embracing some of these data-driven approaches together with complementary equation-driven NWP.
Right. So thank you so much, Dave, for this last question. We are almost at the top of the hour, so I would like to wrap it up. I want to thank Dave for this really informative presentation, and audience for your attention and great questions, a lot of great questions. As I mentioned earlier, an email will go out once the video file has been posted, and we will answer, or Dave will answer, the questions that we didn't get to during the webinar. The next webinar is from the joint GPST ESIG webinar series, and it is called An Imbalanced Reserve Product to Manage Uncertainty Between the Day-Ahead and Real-Time Markets. And it will be held next week on January 31st, and will feature James Friedrich from California ISO. Further information on all of our webinars and meetings can be found on our website at www.esig.energy under events and our newsletters and informational emails. And you all are invited to attend. Dave, thank you once again. And everybody, thanks for your interest. We look forward to seeing you again in the near future. And in the meantime, everyone, take care, stay safe, and thank you all for your participation. See you soon.
Thank you, Julia. Thanks, everybody.